Most of us think of fiber communications as a big business. It covers long distances. It involves large amounts of transmission line. It employs thousands of people and is worth billions of dollars. But all fiber communications begins and ends with components no larger than a grain of sand. It is amazing to think that such a small speck can transmit or receive thousands of telephone calls, video signals, or computerized data. Optical sources and detectors packaged with other electronics to form transmitters and receivers are the most important elements in any fiber system. Without them, the fiber itself is just so much glass. In this program, we will take a closer look at the electro-optic interfaces that are so vital to a reliable fiber system. In any fiber optics communication system, electrical signals, either analog or digital, must be converted to optical signals before they can travel on a fiber. At the other end of the fiber, the optical signal is converted back to an electrical signal. The atoms that make up materials like silicon have electrons that swarm around their cores, forming orbitals or shells around the nucleus. Depending on the number of electrons an atom has, a number of shells can be present. The outer shell, also called the valence shell or valence band, prefers to hold 8 electrons, forming a stable configuration. Atoms having less than 8 valence electrons like to bond with other atoms, so their valence bands share electrons forming various chemical compounds. In order to flow as current, an electron must be free from the valence band and able to move around the molecular structure of the material. Such a free electron is said to be in the conduction band. How easily electrons can be freed from the valence band determines how good a conductor the material is. Transmitters and receivers used with fiber contain semiconductor components. A semiconductor has electrical properties that fall between good conductors like copper or gold and insulators like plastic. An input of energy is required to move a valence electron to the conduction band. When this occurs, energy is also emitted. In the case of LEDs or laser diodes, the energy is in the form of a photon. The exact amount of energy released is equal to the difference in energy levels of the conduction and valence bands. This also determines the wavelength of the emitted photon. The greater the energy, the shorter the wavelength. This graphic shows the ways that energy is transferred in the transitions between energy levels. In the first example, an electron moves from a lower to a higher energy level with the absorption of energy. The second example shows an electron randomly moving from a higher to a lower energy level, emitting a photon of a specific wavelength. This is known as spontaneous emission. In the third example, a passing photon interacts with an electron in a higher energy level, stimulating the emission of an identical photon as the electron drops to a lower energy level. Stimulated emission can only occur if the passing photon contains the exact amount of energy that will be emitted in the transition. The wavelength of both the photons will be identical because they carry the same amounts of energy. In addition, the waves of both photons will be in lockstep with each other. The waves are said to be coherent. Stimulated emission is the basic operating principle of lasers. The word laser is an acronym for light amplification by stimulated emission of radiation. All semiconductor devices use a basic structure called a p-n junction in their operation. This includes diodes and transistors, as well as LEDs, lasers, and photodetectors used with optical fiber. Silicon atoms with their 4 valence electrons bond together to form the crystalline structure of solid silicon. Silicon atoms form covalent bonds with their neighbors by sharing their valence electrons. Each atom has access to a full valence shell of 8 electrons, 4 of its own and 4 from surrounding atoms. This is a very stable condition with no free electrons available. If a material containing 5 valence electrons is added to pure silicon, electrons are left over after all the bonds are made. These extra electrons can now move freely about the crystal. Because the material now has an abundance of negatively charged free electrons, the material is called N-type. If, instead of using a dopant containing 5 valence electrons, we add a material containing 3, the situation is reversed. One of the covalent bond sites will not be filled, leaving a hole. Although holes themselves cannot move, they are in fact charge carriers like electrons, but exhibiting a positive charge. The semiconductor material we have created is p-type. A piece of silicon can be doped with both p and n-type materials, forming a p-n junction. At the junction, electrons can pass across from the n to the p material, combining with the holes on the other side, known as recombination. Both the electron and the hole disappear as charge carriers. Because of recombination, no charge carriers exist in the depletion zone near the junction, forming a barrier to current flow. The barrier prevents further movement of electrons across the junction unless energy is added. When sufficient energy is applied, electrons are injected into the depletion region. This forces electrons already there to move into the holes on the other side of the junction. The junction is now said to be forward biased. When electrons recombine with holes in an LED or laser, photons are produced at wavelengths depending on the band gap of the material. Light-emitting devices use elements from groups 3 and 5 of the periodic table that have 3 and 5 valence electrons respectively. Combining such elements in equal proportions creates a material similar to silicon with stable covalent bonds and no free electrons. By altering the proportions of the group 3 and group 5 elements in a particular crystal, a p-n junction can be created. Gallium arsenide is one example. Its band gap between energy levels produces infrared light when holes and electrons recombine. Semiconductors like gallium arsenide are used to fabricate LEDs, both for general purpose use and for use with optical fiber. The LED in this example is made from a single type of semiconducting material. As such, it is known as a homojunction device. It emits light from the edges of the material as well as its entire surface. The result is a low-level omnidirectional light output unsuitable for most fiber use. Only a small portion of light can be coupled into the fiber, with the rest going to waste. However, because of its low cost, this type of LED does find use in low-performance, short fiber links. A p-n junction can be created using a number of semiconductor materials having similar crystalline properties, but with different energy levels and refractive indices. Known as a heterojunction, this structure confines the charge carriers to a particular region of the chip, resulting in more directional light output. The use of semiconductor materials with differing refractive indices allows the LED itself to function as a waveguide, producing maximum coupling efficiency to optical fiber. LEDs operating at the 820 nanometer window are usually made from gallium aluminum arsenide. Longer wavelength devices for the 1300 and 1550 windows may use gallium indium arsenide phosphide and other materials from group 3 and group 5 of the periodic table. But no matter what materials are used, the output of an LED consists of a small range of wavelengths rather than a single wavelength. The spectral width of the output is due to slight differences in actual energy levels in the conduction and valence bands, resulting in photons of differing wavelengths. For high-speed digital fiber systems, this spectrally wide low-power output may not be suitable, requiring the use of a laser instead. We have already seen how photons identical in energy and wavelength can be produced by stimulated emission. In a practical laser device, the light-generating material is placed between a set of reflectors that have been aligned perfectly parallel to each other. The optical cavity formed by the aligned mirrors is called a Fabry-Perot resonator. As energy is applied to the light-generating substance, also called the lasing medium, photons are spontaneously emitted as in an LED. Some of the photons pass through the sides of the material and are lost. However, at some point in time, a single spontaneously emitted photon will stimulate the emission of an identical photon from an excited atom. The two photons will stimulate the emission of two more, and so on. The ever-increasing stream of identical photons strike the mirrors and are reflected back into the lasing medium. stimulated emission increases until it reaches an equilibrium depending on the type of laser medium used and the amount of exciting energy available. The structure of a laser diode is similar to an edge-emitting LED. The resonant cavity is formed by cleaving the end faces of the semiconductor material to form parallel, highly reflective facets. In semiconductor lasers, a beam is available at both reflectors. A photodetector can be placed at one end of the laser chip to monitor beam power, allowing drive circuitry to keep the output level stabilized. In order for laser action to occur, the input energy to the device must exceed a certain threshold. Below the threshold, only spontaneous emission is produced, as in an LED. Because every photon generated by stimulated emission is identical to the one that triggered the process, the laser beam consists of coherent light. All waves in the light beam are in lockstep. The laser beam is highly directional and does not spread out as rapidly as the beam from an LED. The laser output is nearly monochromatic, consisting primarily of one wavelength. Even in a laser, light of differing wavelengths can be present in the output. There are two reasons for this. First, because of slight energy level differences between individual atoms, photons of slightly different wavelengths will be emitted. This shows up as a broadening of the laser's spectral width. Second, some of these photons of differing wavelength may trigger their own stimulated emission processes. This is like having a number of lasers of slightly different wavelength operating simultaneously. An optical spectrum analyzer shows these side modes on either side of the center wavelength of the laser. Both of these effects cause an increase in spectral width of the laser output that lowers the quality of the device. Because light of varying wavelengths travels through a fiber at different velocities, spectral width is the main limiting factor of high-speed single-mode systems operating over long distances. For this reason, intense research and development has been devoted to constructing reliable lasers operating on a single wavelength. The distributed feedback, or DFB laser, uses an internal grating to allow only photons of one wavelength to reach the reflectors, thus suppressing the development of side modes. In some fiber systems, like those using wavelength division multiplexing, it is imperative that the optical sources used have a very narrow spectral width and stable center wavelengths. This is required to ensure that the receiving equipment can separate the optical carriers. Tunable lasers generate a center wavelength that is adjustable over a limited range. This is done by using a movable diffraction grating instead of a simple reflector at one end of the optical resonator. The grating is controlled by a piezoelectric crystal that moves slightly with applied voltage, allowing a desired wavelength to be selected. Lasers are very sensitive to temperature changes and power supply quality. Their output can change significantly in both intensity and wavelength for a minuscule change in temperature. Even small lasers packaged with drive electronics can dissipate over a watt of heat. For this reason, thermoelectric coolers using the Pelchet effect are added to stabilize the temperature of the laser package. The Pelchet cooler is controlled by a closed-loop temperature servo system using a thermistor to sense the temperature of the laser and adjust it accordingly to keep it within a fraction of a degree. The hot side of the cooler is thermally connected to the outside of the laser package, so adequate heat sinking must be provided. Semiconductor lasers are also available in chip form for integration into various package designs and as single components in the popular TO-style transistor case. It is up to the user to provide temperature control for these devices. Although most semiconductor lasers operate at around 1.5 volts, special consideration must be given to power supply design. Lasers are extremely sensitive to transient voltage spikes that occur at turn-on or turn-off, or transients that may leak in from the AC power line. Even one transient of sufficient magnitude may destroy or severely impair a laser diode, so the power supply must be constructed to eliminate them completely. Back reflections generated in fiber systems can find their way back into the laser cavity, disrupting the stimulated emission process. To prevent back reflections from causing transmission errors, an optical isolator should be inserted between the laser and the fiber system. The packaging of optical sources for fiber use must efficiently couple optical energy into the fiber. Because a fiber will only transmit light launched into its numerical aperture, the source must ensure that most of its output is accurately targeted on the fiber's core. A surface-emitting or Burris LED has a large emitting area, so only a small amount of light may be coupled into a fiber. Edge-emitting LEDs guide light toward the edge of the chip, making fiber coupling easier. Laser devices are best suited to fiber coupling because the well-collimated beam emerging from the edge of the chip does not spread out appreciably before entering the fiber. A micro-lensed source uses a small glass bead epoxied to the emitter chip to focus diverging light rays onto the fiber end. Burris LEDs often have a small well etched into the chip where a fiber pigtail is epoxied in place. Other devices using pigtails have them aligned very close to the emitting surface of the chip. The closer the pigtail is to the emitter, the more light can enter the fiber before it can spread out and be lost. Sources can also be packaged in receptacles designed to mate with popular fiber connectors. The choice between LED and laser will depend on the type of fiber system being designed. For example, edge-emitting LEDs are the optimum choice for LAN systems, including Ethernet, token ring, FDDI, and ATM systems operating up to 622 megabits per second. The output of an LED can be varied in a linear fashion with applied forward bias current, making it ideal for modulating with analog signals. The laser diode is not as suitable for analog because its output does not usually vary in a linear fashion with applied drive current. For this reason, care must be exercised when selecting lasers for analog applications. Manufacturers' data sheets must be consulted with regard to device linearity. Laser diodes inherently have high switching speeds, making them perfectly suited for the fast on-off pulsing of digital transmissions. The bandwidth that a given source can handle depends on the rise and fall times of the device. That is, how quickly the semiconductor will respond to on-off pulsing. Rise times are measured in nanoseconds. The bandwidth the source will handle can then be approximated by this equation. For laser diodes with rise times less than 1 nanosecond, bandwidth will be in the gigahertz. An LED with a rise time of several nanoseconds will have a bandwidth of only megahertz. The choice between LED or laser will also include total fiber distance, the allowable number of repeaters in the system, as well as cost and reliability factors. The great power level offered by lasers allow greater distances with fewer repeaters. However, lasers generally cost more than LEDs and have lower mean time between failures. When used in fiber-rich systems, source bandwidths can be slower because more fibers can be used to carry the signal load. Thus, lower speed lasers or even LEDs could be used. However, in high-speed multiplex systems such as Sonnet, high bit rates make lasers the only choice. Because lasers produce high-power, well-collimated beams that do not spread out rapidly, the possibility of eye damage is a very real threat. Lasers are classified into groups depending on the wavelength and power level they produce. Most lasers used in communications fall into the lower power class 1 and 2 groups. However, as fiber systems become larger and more complex, higher power lasers are being used more routinely. Anyone working with fiber systems must allow some simple guidelines to prevent eye injury. Never look directly into any optical port, and unused optical ports should be always capped. When working on systems containing lasers, safety glasses that attenuate the proper laser wavelengths should be worn. Finally, never splice or connectorize a fiber unless the optical source has been switched off. Further information regarding the safe use of lasers is available in the safety videotape of this series. As advanced applications push fiber to the curb, to the home, and to the desktop, there is an increased need for a powerful but low-cost light source which can be modulated to provide data rates of gigabits per second. A good example of this gigabit Ethernet, where the data rate exceeds the capability of LEDs,
yet this application demands low-cost components. The vertical cavity surface emitting laser, or VCSEL, combines the best features of LEDs and conventional lasers to meet this challenge. VCSEL devices can be manufactured by bonding wafers of gallium arsenide to form an active or light-generating region, as well as mirrors to form the laser's resonator. This is similar to common LED manufacture and results in low cost with high yield. In addition, VCSELs feature low power consumption, reliable room temperature operation, and can be tailored to provide circular beam profiles for better light coupling into optical fiber. VCSELs are multi-mode devices and cost the least to manufacture at 850 nanometers. However, they can be produced for wavelengths up to 1600 nanometers with output powers ranging from Class 1 to Class 3. VCSELs are highly compatible with low-cost pin detectors and are commonly available in connector packages for simplex, duplex, and ribbon configurations. They also perform well in plastic optical fiber systems.
At the opposite end of the fiber system is the receiving equipment, the heart of which is the optical detector. Detectors perform the opposite function of optical sources. They convert a flow of photons to a flow of electrical current. The simplest form of photodetector is the PN photodiode. Photons can be absorbed by semiconductors, moving electrons from the valence band to the conduction band and creating electron-hole pairs. In order for a photon to be absorbed, its wavelength must match that of an energy level transition the material is capable of. Thus, certain materials can only absorb photons of specific wavelengths. For this reason, source and detector wavelengths must be matched. Photodiodes work like LEDs in reverse. First, the photodiode must be reverse biased with negative connected to the P-type material and positive to the N-type. In this condition, no current flows in the circuit because a large depletion region forms at the junction, resisting the flow of current. If incident photons strike the device at the depletion region, the resulting electron-hole pairs separate and quickly move to their respective regions. This movement shows up as a current flow in the external circuit. If incident photons strike outside the depletion region, the resulting electron-hole pairs move slowly towards it. Many of the carriers recombine before reaching the depletion region, while the carriers that do reach it are quickly swept across. This results in external current flow that is delayed. Such slow response make the PN photodiode unsuitable for fiber systems. The PIN diode was developed to overcome the limitations of the simple PN diodes. A PIN diode consists of a layer of intrinsic semiconductor sandwiched between the P and N layers of a PN junction. The intrinsic layer is semiconductor that has not been doped as either N or P material, so it does not contain free charge carriers.